Conservative vector fields. Some vector fields can be represented as the gradients of differentiable functions and some cannot. Those that can are called conservative vector fields. The definition of a conservative vector field is as follows. A vector field F, again we're using a bold F that indicates it's a vector field, is called conservative if there exists a differentiable function F, that's a lowercase f, such that that vector field F is equal to the gradient of that F. The function F is called the potential function for F, the capital F, the vector field. So recall the gradient of a function of x and y. If the function of x and y equals sine 3x cosine 4y, and we take the gradient of that, that gradient is considered to be a conservative vector field. Now recall, to find the gradient, you take the partial derivative with respect to x. You treat x as a variable and y as a constant, so the derivative of the sine 3x is cosine 3x times 3 times that cosine 4y. And then that's your first component of the gradient vector. The second component is found by taking the partial derivative of this with respect to y. Treat y as a variable and x as a constant. The derivative of cosine of 4y is going to be negative sine of 4y times 4 times that constant sine 3x. So this bold capital F is a vector field. This is the gradient of this f of xy, that lowercase f. F of xy right here is called the potential function, and capital F in bold is the conservative vector field because it is the gradient of that potential function. The vector field given by f of xy equals 2xi plus yj is conservative. To see this, you want to consider what possible potential function exists so that if you take the gradient of it, you end up, the result is 2xi plus yj. Well, if we look at this potential function, f of xy equals x squared plus 1/2 y squared, later on we'll get into how you find that potential function, but for now, look at this potential function and determine if this is indeed the gradient. When you find the gradient, you take the partial derivative of this with respect to x, and that's going to give you 2x, and the partial derivative with respect to y would give you y. So this is indeed a conservative vector field because this is the gradient of this potential function. Okay, the following important theorem gives a necessary and sufficient condition for a vector field in the plane to be conservative. The test for conservative vector fields in the plane: let M and N have continuous partial derivatives on an open disk R. The vector field bold f of xy equals mi plus nj. M and N are components of the vector field F. We say it is conservative if and only if the partial derivative of n with respect to x is equal to the partial derivative of m with respect to y. And that gets into the mixed partial derivatives are always equal for a function of two variables. So we're looking at the components of the vector field. We take the partial of n with respect to x. If that is equal to the partial of m with respect to y, then we know the vector field is conservative. And if it is conservative, then we can find a potential function. If it's not conservative, you wouldn't go through the trouble of finding a potential function. Let's decide whether the vector field given by these vector functions is conservative. For the first one, A, our vector field is x squared yi plus xyj. We want to take let the m be x squared y and the n be xy. You want to take the partial derivative of xy with respect to x, and that's going to be y, and take the partial derivative of x squared y with respect to y, and that's going to be x squared. Now that's not going to be equal, so that one is not conservative. I'll go through the steps in just a second there. If we look at this one, part B, take the partial of y with respect to x, and you get 0, and the partial of m with respect to y, and you get 0. So this one is going to be conservative. Again, I'll go through the steps in just a second here. The work for part A, again, you're taking the partial derivative of x squared y, this one with respect to y, you get x squared, and this one with respect to x is y. These are not equal, so part A is not a conservative vector field. Okay, for part B, again, here's our vector function. We take the partial of 2x with respect to y, we get 0. The partial of y with respect to x, and we get 0. These are the same, so we can say that vector field is conservative. So we could actually find a potential function where if you take the gradient of that function, the result is going to be this vector field. Okay, we'll do a few of these examples. I'd like you to pause the video, try this one on your own, test to see if it's conservative. And if it is, I'm going to go through the steps of how we find a potential function. Okay, so here we have our vector field. And again, F is a vector field that has components mi plus nj. We say this is conservative if the partial derivative of n with respect to x is equal to the partial derivative of m with respect to y. If that is equal, then we could say that f is conservative. Okay, if those two partial derivatives are equal, then we can say f is conservative. Now, I do want to point out here that when you see the vector fields in textbooks or in prints, you'll see the bold f. When I write it out by hand, I use the vector notation with the little bar above the vector field. So just keep that in mind. Also want to point out that these are the partial derivative symbols here. I tend to look like the number 2. I'll try my best to avoid making that look like the number 2. So let's start off with our m. Our m is 1 over y. And we can also write that as y to the negative 1 power. We want to find the partial derivative of m with respect to y. And that partial derivative is negative 1 over y squared. Now let's look at our n. Our n is equal to 2x over y squared, or we can even say this as 2 over y squared times x. And we want to take the partial derivative of n with respect to x. We treat the x as a variable and the y as a constant, so this is really like a big constant times x. So that partial derivative is 2 over y squared. These two partial derivatives are not equal, so we say that that vector field, that original vector field, is not conservative. Okay. Now the question does say, if so, if it is conservative, find the potential function. We don't want to find a potential function here. There is not one that exists where this is the gradient, so we don't even have to do that step. Okay, so here's another example. Determine if this vector field is conservative. If it is, let's find the potential function. Pause the video, try this one on your own first, and then come back and check your work. Again, the vector field F is going to have that components mi plus nj. So the test here is to determine if the partial of m with respect to y is equal to the partial of n with respect to x. Then we can say then that f is conservative. So in this case, let's find our m here is 3x squared y squared. The partial of m with respect to y, we treat the y as a variable and x as a constant. That's going to be the derivative of y squared is 2y times the 3x squared. That is going to be 6x squared y. The n part of this vector field is equal to 2x cubed y, and we want to take the partial derivative of n with respect to x. We're treating the x as a variable, y as a constant. So the derivative of 2x cubed is 6x squared times this constant. Now since these two are equal, then we can say yes, f is conservative. And if it is conservative, we want to find the potential function. All right, now I'll show you how we go about finding that potential function. What you're going to do is take the antiderivative of m with respect to x and take the antiderivative of n with respect to y. And we're going to use those, combine them so we can find the potential function f of x comma y, where if you took the gradient of this potential function, you would get the vector field f. So let's begin with the antiderivative of m, which is 3x squared y squared. Take the antiderivative with respect to x. Treating x as a variable, you're going to add 1 to the exponent and divide. So this is going to be x to the third times y squared plus a constant. Now this is where we do things a little bit differently here. When we take the antiderivative with respect to x, we're treating y as a constant. So when we add a constant here, we're not going to simply just add a c like we do with just basic integration. We are going to add g of y, which means that this is a function of constants or a y. So instead of that plus c that we used to use, we're going to add a constant, but that constant could also have y's in it when we're taking the antiderivative with respect to x. We're treating y's as constants, so there could theoretically be a y added to that function. Now let's go ahead and take the antiderivative of n with respect to y. So let's take the antiderivative 2x cubed y with respect to y. Treating y as a variable is you're going to add 1 to the exponent here, divide, and that will give you x cubed y squared plus, when you're taking the antiderivative with respect to y, you're treating y as a variable, x as a constant. So instead of just adding a constant c, we want to add a function of constants that could also include x's in it. Now we're going to combine these. So anything that they have in common here is going to be part of the potential function. So our potential function, they both have this x cubed y squared. We only put that one time in our potential function. Now here we could have a constant with y's in it, but notice there are no other y's listed in the other antiderivative. Or we could have, in this case, we could have other x's, but we don't see any of those. So in this case, it is a simple plus c. That is not always going to happen. We do want to make sure we integrate each one of these with respect to x or y, and even later on with respect to z. So this right here is called the potential function. And what that means is that the gradient of this f of xy, that potential function, is equal to the vector field f of xy.